The next way to measure relationship between two random variables is called Pearson correlation coefficient. Pearson correlation coefficient. Let me first write the mathematical formula for PCC. It's also called PCC, just as a short notation. It's often represented with the Greek alphabet rho. So the Pearson correlation coefficient between two random variables x and y is nothing but the covariance of x and y divided by the standard deviation of x and the standard deviation of y. Now you might ask, why is this? Why are we defining a new metric by just using covariance? We just learned about covariance. One of the problems with covariance is covariance doesn't take into effect what is the variability, right? What is standard deviation of x? Standard deviation of x is nothing but square root of variance of x. So when you measure covariance, you're not measuring what is the variability within x and y. So PCC is a small modification on covariance itself by just dividing your covariance by your standard deviation of x and standard deviation of y. But it gives us good value. It gives us interpretability. So one problem with covariance that we just understood a while ago is that I know that if as x increases, if let's say as x increases, let's assume y also increases, then, right? Then if this is the case, then covariance is going to be positive. But how much positive? It could be very, very positive or very negative, right? Similarly, I know that as x increases, y decreases, my covariance is going to be negative, right? But I don't know how negative. So PCC is a very nice idea. Let me show you a simple example of PCC. So this is the Wikipedia page for Pearson correlation coefficient, as you can see here. And we'll use Wikipedia extensively, as I've mentioned earlier. Now let's look at this, right? If your data set is such that, okay, let's take this example first, that all your data points, let's assume this is your random variable x, this is your random variable y, right? And as x increases, if y increases, also that they lie perfectly on a straight line, let's say, which means it's a perfect increase, perfectly monotonically increasing, then your PCC or your rho for that is going to be +1, exactly +1, right? And remember, your correlation coefficient, Pearson correlation coefficient is going to lie between -1 and +1. Unlike your covariance, your Pearson correlation coefficient is bound between -1 and +1. And if your data is perfectly correlated, and if all the data points, which are your orange dots here, lie on a straight line, on a perfect straight line, then what you get is a rho of 1, right? Now what happens if as x increases, this is the case where as x increases, y also increases, right? In this case, on the other hand, as x increases, your y is reducing. Again, very perfectly, everything falling on a straight line. Then your rho is going to be -1, right? The next question is, since we know that rho lies between -1 and +1, what happens in a case like this, where this is your x and this is your y? Of course, you can quickly see from here that as x increases, your y is increasing, but these points are not lying perfectly on a straight line. In such a case, your rho is going to be positive. It's going to be greater than 0, but it's also going to be less than +1, right? Similarly, if you have this relationship where as x increases, your y reduces, but not perfectly in a straight line-ish fashion, right? Then your rho is going to be less than 0, but still greater than -1. When does rho become 0? That's an important question to ask, right? Rho becomes 0 when there is no relationship between x and y, right? For example, if I take x to be my heights, right, and if I take y to be my grades in an exam, the marks that I get in an exam, there is no relationship between them. It doesn't mean that taller students will perform better or shorter students will perform better. There is no relationship between these two random variables, right? In such a case, you'll get a rho of close to 0. Now, you might ask, okay, this has solved all of our problems. Not exactly. So, Pearson correlation coefficient, while it's very powerful, remember, it's going to be perfectly equal to 1 only if they lie on a line. So, your Pearson correlation coefficient and covariance have a bias towards linear relationships. So, which means they're going to give you a very good value of either +1 or -1 when the relationship between your random variables x and y is perfectly linear, right? Now, let's look at a bunch of examples where Pearson correlation coefficient does not perform very well, or it has its own limitations. Okay, let's look at this very nice example, right? If as x increases, if y also perfectly increases, you have a Pearson correlation coefficient of 1. But if you have your data like this, where as x increases, y is increasing, but not in a perfect linear fashion. There are points slightly away from your perfect line. Then you get a Pearson correlation coefficient of about zero point 0.8. As this ball-like structure becomes flatter and flatter, right? Like for example, if this ball becomes like this, right, between your x and y, certainly there is some linear relationships, but there are a lot of points which do not fall into this linear relationship. In such a case, your Pearson correlation coefficient, while it's positive, it's going to be closer and closer to 0. Of course, for a data set like this, where there is no relationship between x and y, right, you're going to get a value of 0. Similarly, if it has, this is perfect -1, and as you come towards 0, so as you're going towards from +1 towards 0, your variance on this axis is increasing, right? The ball-like structure is getting more from an ellipse, it's becoming closer and closer to a circle, which means there is lesser and lesser relationship. And similarly this way. The other thing with Pearson correlation coefficient is it doesn't matter if your relationship, if your line, right? Because this is your x and y, right? The slope of this line doesn't matter. Whether this line is like this with a larger theta here or a smaller theta, it really doesn't matter. As long as the relationship here, it's almost close to this theta is much smaller than these two thetas, right? But Pearson correlation coefficient doesn't care about it. All that it cares about is whether there is a linear relationship or not, or either an increasing linear relationship or a decreasing linear relationship. So this is one of the cases where it's not telling me exactly how fast is one random variable increasing with respect to other random variable, right? Because we are not using slopes here, right? Because for any slope, these points have different slopes. Sorry, these lines have different slopes, and still you get a PCC of 1 or -1. The third type of very interesting relationship is, let's assume my random variables are like this. Let's assume this is my random variable x, this is my random variable y. If you give this to a 5th grade student, he would say, yes, there is some relationship between x and y. Of course, it's not simple to say. It's not like as x increases, y increases. This is like a sine wave, right? But there is a relationship. And the problem is Pearson correlation coefficient cannot capture complex nonlinear relationships like this. This is a nonlinear relationship, right? Because in this region, this is, of course, this could just be, I could write this relationship as y equals to, let's say, sine of x plus some error, because it's not perfectly sine of x, because there are some errors here, small error, okay, a small error. But if you show this to a 5th grade student, he would say, oh, there is this wavy relationship. Of course, he may not know sine theta because he hasn't studied trigonometry yet. But if you give it to a 12th grade student who might have studied some trigonometry, he would say, oh yes, this looks like a sine curve. So there is actually a relationship between x and y. It's just that it's not linear, and hence Pearson correlation coefficient will give it a value of 0. So Pearson correlation coefficient, your covariance, and all the metrics that we're discussing right now will not be able to find relationships like this. To find relationships like this, we actually build full-fledged models. We build something called regression models that we learn when we learn actual machine learning, which is very elegant and beautiful, right? Similarly, if you look at this, there is also a relationship between x and y here, right? This is sort of like a quadratic relationship, right? Where in this region it's reducing in this region. So this I can write it as y equals to, let's say, x square, right? If this was 0, right? Plus an error, because it's not exactly here. There are some points which are slightly away from here. So that's why I'm writing the error term here. So there is actually a relationship between y and x. Anybody who studied coordinate geometry and conic sections will understand, because this is like an elliptical pattern, right? But your Pearson correlation coefficient will never be able to detect it. That's one of the big limitations of Pearson correlation coefficient. Now there is one more data set that I wanted to show you, so as to motivate you about our next idea. So again, this is the page for rank correlation coefficient, Spearman rank correlation coefficient on Wikipedia. And let's look at this. So here, let's assume I have a relationship like this, right? Sort of where, okay, as X increases, my Y is increasing, but there are some areas where it's flatter, where the relationship is not very strong. There are areas where the relationship is strong like this, right? As X increases, Y is increasing. Except that in this case, as X increases, Y is increasing, but not linearly, right? This is not like a perfect line like this. It's not like a perfect line. So in these cases, what happens is Pearson correlation coefficient, even though this is monotonically increasing, right? So what does monotonically increasing mean? It means that if you take any 2 points on x-axis, if this value is greater than this, then this value, the corresponding y value, is going to be strictly greater than equal to this. Strictly greater than this. That's called monotonically increasing, right? So what is monotonically non-decreasing mean? It means if you take any two values here, right, the corresponding y's. So if let's take two values, x1 and x2. Let me define it more rigorously. And for x1 and x1 and x2, let's say I have y1 and y2. If let's say x2 is greater than x1, then if y2 is greater than equal to y1, if this relationship always holds, it's called monotonically non-decreasing, right? On the other hand, if as x2 increases, if let's say my y2 also increases, then it's called monotonically increasing. Here the only difference here is there is a greater than here, while here you have a greater than equal to. So this is strictly monotonically non-decreasing, because if you take two values here, your x's may be different, but your y's are roughly the same, right? So if you take a function like this, if this is the relationship between your random variable x and y, you expect your Pearson correlation coefficient to give you a value of 1. But what it does is it gives you a value of 0.8. That's because this relationship is not linear. And how do we fix it? We fix it using our next concept, which is Spearman rank correlation coefficient.